So I'm going to record and make a screencast for everybody because this is a classic problem. Would someone read number 6, please? Thanks, Sam. And I'll write a givens list while he does. Maybe you could help me with the givens. Yeah.
What is the acceleration?
Whoa. What is what?
What is the acceleration?
All right, I got that given. What else?
20 kilograms.
20 kilogram. What's that?
That's the mass.
Good. What else you got?
Cement that is pulled upwards.
Okay, so pulled upwards. I'm going to make it a rope pulling the cement upwards, right?
Yes.
So there's my cement being pulled upwards. Are you guys cool with that?
Yeah.
And so this rope has a tension of 300 newtons. Is everybody good? All right. You might see a little better if you turn off that light. What else we got to do? Next step. Any ideas? All right, very good idea. Choose a system, make force diagram. What forces are acting, please? Tension up and weight down? All right, and I should probably find out which way my acceleration is. I know I've got acceleration because it should be up probably, yeah. And let's see if that makes sense. That would mean the force up has to be larger than the force down. Am I right? I drew that a little too long. How's that look? So there's my weight, and there's my tension due to rope. That's my rope pulling up, earth pulling down. All right, and actually, if you know the mass, you also know the weight, because weight is m times g, where g is 10 newtons per kilogram, right? So the weight is going to be mass, which is 20 kilograms, times 10 newtons per kilogram, which is what?
200.
So I got a force of 200 newtons of weight down. I might as well label that 200 newtons down, and it looks like I have 300 newtons up. So does this make sense with acceleration being up? What would you do next, home chickens? Head to tail? Okay, so you're adding the forces. Very good idea. So there's tension up. I'm just copying it. Tension up. And then weight down, I'm just going to draw it shorter. Are you guys cool? And I'm going to replace weight with m times g, which is my 200 newtons down. And then what are these forces going to add to? The net force has to be which way, up or down? Okay, very good. So we got a net force up. There's my net force up. And what can I label my net force? Based on Newton's second law, which is net force equals ma. What do I label net force, please? I don't hear you guys. What can I label my net force vector? What's its length in terms of m and a? What's the, oh, you're giving me the number. You're right, probably. M times a. I just meant please label this vector ma. Are you guys good? What are we solving for here? All right, so I'm going to write ma equals, and then you're going to help me write an equation for that. T what? Minus or plus mg? It would be T minus mg, right? I'm looking at the length of the tension. You only need to look at the lengths of the arrows. And if you look at the length of the tension, you could have written it 3 different ways. Maybe that'll help you. You could have written tension equals mg plus ma. Did you guys see how I got that? I'm looking at this diagram. So the length mg plus the length ma has to be the length of my tension. Another way I could write it is mg equals, see if you understand it. What could I do here? T minus what? ma. Yeah, that's another way I could write it. These are equivalent mathematical statements. They're all correct. Are you guys good? Yeah. Felix, go.
Oh, on the circle thing?
Yeah, that's a vector sum diagram where we add the forces.
How did you know the MA is going up?
How do we know ma is going up? What a brilliant question. Yeah? One way is acceleration is going up, and your net force has to therefore be up. And ma is the magnitude of your net force. The other way you can argue it is, do you see that your ma vector goes from tail to tail? the tail of your MA vector is at the tail of T, and it ends at the head of MG. Do you guys see the problem's basically solved?
Yeah.
I'm going to go ahead and finish it, and I'll post it. Keep practicing. It will pay off big time. Have a great day. So, if I use that one, I got MA equals T minus MG. I got A equals T minus MG over MA. And now I think I have everything to solve, right? I can plug in for T is 300 newtons. MG looks like it's 200 newtons. And then, okay, I made a mistake here. Hold up. Totally made a mistake. Let me go back a couple steps. Whoops. There we go. Oh, I went too far back. Okay, so A equals T minus MG over M. There it is. A is going to be, what's T again? 300. MG is 200 over M. What's M again? 20 kilograms? So this is like 100 newtons over 20 kilograms, which is basically 5 meters per second squared. See, what most people do in this problem is they just go straight to Newton's second law, and they do the whole thing wrong. I'll just show you in this window. Take care. They go like this. They go A is F. They don't even write net force there. They write F over M. And then they put in 300 newtons there because they know that's a force, 300 newtons over M, 20 kilograms. And they get like A is, what's that? 30 over 2, that's 15 meter per second squared. So that's totally wrong. You don't want to just go straight to Newton's second law and plug stuff in. What you want to do is go through the process of force diagram, force diagram. It'd be even better if we'd add a little motion map here, right? Show what's happening with your velocity for real. That's what's happening to my velocity, right? And then this would be my acceleration vectors. And then, so you could do motion map with your diagram, you do your force diagram, you do your vector sum diagram, and then you use your vector sum diagram to create an equation. And you'll notice that you'll get it right every time that way. This all depends, the solution depends on your vector sum diagram. That's where it comes from. And you think about it, you surely have to add forces as vectors in order to use second law. Second law depends on you actually adding forces as vectors and treating them as vectors where you respect their direction. Anyway, have a good day. Thanks for watching.